Hey everyone. After finishing our discussion of linear transformations, we're now moving on to logarithmic transformations. Okay, and the basic idea behind logarithmic or in general nonlinear transformations is that as soon as we have violations of the basic assumptions of additivity and linearity that we talked about in the context of linear regression assumptions, if either of those assumptions are not reasonable in the context of the data or the data generating process that we have and the outcome that we want to predict, then some kind of nonlinear transformation can sometimes remedy that situation. And a very common one to use in cases like that is the logarithmic transformation, and particularly using a logarithmic transformation for the outcome measure. Okay. In general, it commonly makes sense to take the logarithm of outcomes that are all positive. Okay, and if we think about this from a kind of predictive prediction point of view, this makes quite a lot of sense, because if we have an outcome measure that is all positive, we want to make sure that whatever predictions we're making about this outcome measure are all positive as well. If we just model an all positive measure using linear regression, there are no restrictions on our predictions that constrain our predicted values to be, only in the positive range, right? So by taking the logarithm of our kind of all positive outcome measure and modeling the outcome on the logarithmic scale, where it's not bound between, where it's basically ranges from minus infinity to plus infinity, we can kind of make predictions on the logarithmic scale that is not restricted, and then take the exponent of that, and that exponent of that log variable will then be only bound in the positive range, right? So by taking the logarithm and modeling the outcome measure on the logarithmic scale, we're basically taking into account that on the original scale, we're only making positive predictions, right? So in that sense, it often makes sense to take the logarithm as soon as we're working with outcomes that are all positive, okay? There's another reason, and I mean there are other kind of attributes and other kind of effects of the logarithmic transformation. For example, it kind of compresses very extreme values to be kind of closer to the distribution. So whenever you have a very skewed distribution, the logarithmic transformation to some extent also kind of corrects for these kinds of skewed distributions. But one of the prime reasons why you use the logarithmic transformation or want to model an outcome on the log scale is not necessarily to achieve a more or less skewed distribution, but rather that kind of corresponds to an underlying data generating process where we're actually thinking about the effects or the coefficients as part of a multiplicative model rather than an additive model, right? So a linear model on the logarithmic scale corresponds to a multiplicative model on the original scale, right? And it's important to kind of recognize how this kind of implies a different underlying data generating process, right? And to see why this is the case, we can just take a look at a basic logarithmic specification where the outcome measure is logged. If we take the exponent on both sides, of course, we're left with our outcome measure on the left-hand side, and on the right-hand side we have e to the power of our linear or our systematic component, essentially, plus the error term. Now we can pull out or pull apart this sum as a product of exponents, okay? So e to the power of beta 0 will replace as b or capital B 0. E to the power of beta 1 times x1 we'll just write as b, capital B1 to the power of x1, and so on. The key here is that initially on the log scale we have an additive model where each of the predictors kind of is included in an additive fashion. But then if we transform that back on the original scale, we see that now each of these predictors kind of impacts the outcome measure as part of a multiplicative model, right? And what this ultimately does is, with every 1 unit increase in x1, we don't have an additive linear effect, or a linear, and constant difference in the predicted outcome measure, but rather the change in the outcome is ultimately a percentage change or a proportional change depending on the current value of the outcome. Okay, and in order to kind of illustrate this, and I have old videos that I linked on Canvas in the past on interpreting logarithmic transformations and models that include logarithmic transformations. We see that basically as soon as we have a logarithmic or log-dependent variable, we can interpret the coefficient here, at least approximately the coefficient here for beta 1, as the 100 times the percentage change in the outcome measure that is associated with a 1 unit increase in our predictor. Okay, so a 1 unit increase, if we compare two groups of observations that differ only by 1 unit change in the predictor, the predicted difference on the original scale is 100 times beta 1 in percent approximate. This is just an approximation that follows from basically this multiplicative model, essentially. Okay. The key here to recognize is that compared to the linear transformation that we talked about in previous videos, is that with the logarithmic transformation, I'm going to move myself, the logarithmic transformation represents a different data generating process, and thereby whenever we apply logarithmic transformations, we change our model fit and also change our predictions, right? So it's not only about facilitating interpretations of coefficients, we're actually modeling a different data generating process. Okay. And also keep in mind, in most cases, we're talking about taking the logarithm of our outcome measure, but we can also take a logarithm of our predictor. If we have basically a logged outcome and a log predictor, or a so-called log-log model, we're essentially looking at kind of we can interpret that coefficient as the expected proportional difference in y per proportional difference in x. Okay, so whenever we have logarithms on both sides, or a so-called log-log model, it's not a 1 unit change that is associated with a proportional difference in the outcome, but rather a proportional difference in x that is associated with a proportional difference in y. Right? I have some old videos that I linked on Canvas on interpreting these models as well. Right? The key point is this affects the underlying model fit and affects our underlying predictions. Okay. So let's look back at our example of predicting people's salaries and now apply a logarithmic transformation. Now we're predicting logged earnings based on height, still in inches. We're not centering our height variable here. We could, of course, do that, but in our, at least when it comes to interpreting coefficients, this is now, the intercept is now kind of can be interpreted as the expected logged earnings when height is equal to 0. So the logged earnings themselves don't have a direct interpretation. Of course, we can take e to the power of that intercept, but since we don't directly want to interpret those coefficients in this case, we can just use the raw heights, of course. One thing we have to do, though, just to make you aware, we're looking here at a subset of the data. We have to basically discard all observations for which the salary was equal to 0, because, of course, the logarithm we can only take the logarithm of positive values. The logarithm of 0 kind of basically approaches minus infinity. So we have to exclude those observations. Okay. Going forward, we could kind of add like a two-step model where we would model whether or not someone had a salary versus not, and then model earnings based conditional on the salary being larger than 0 to take that into account. But for now, we'll just discard those observations. Okay. So if we wanted to interpret, as I said, the intercept, we don't really want to interpret here. 1, because it's on the log scale, and 2, because height is not centered. So this is again an extrapolation, so we're not really interested in that. Height, on the other hand, we can directly interpret as the percentage change in predicted income for a 1 unit difference in between two groups, for 1 unit difference in height, right? So 1 inch difference in height between two groups is associated with a predicted difference in earnings of about 5%. Okay. We can visualize the relationship between logged earnings and height, both on the log scale, which is right here on the left-hand side, and we can see on the logged scale we're modeling a linear relationship, right? This is still a linear regression, just on the log scale. But we can also then kind of transform that back onto the original scale, and here looking at our earning variable in thousands, and we can see how we kind of fit, similar to the example that I showed you here, now fit this curved line for a logarithm or logged outcome measure. Okay. As I mentioned, taking the logarithm of the outcome measure implies a different underlying data generating process, and essentially implies a different model fit. So one thing we can do is we can compare these models using posterior predictive checks to examine whether or not a logarithm or logging the outcome ultimately leads to a better model fit. And the way we're doing this here, one thing to kind of, just to make sure that this is kind of a fair comparison, what I'm doing here is I'm repeating our linear model with centered height and the interaction with gender, but also just focusing on the subset where earnings are larger than 0, because that's just the data that we considered in the logged outcome measure case. So we're just keeping the observations that are included in the analysis constant across both cases. And then we're looking at our basic posterior predictive checks, where we're comparing the observed distribution of the outcome measure versus the basically posterior predictive distribution of the outcome measure based on a subset of our posterior simulations. Okay, we've looked at examples of that in previous videos. The first thing we do is we create our predictions from the posterior distribution using posterior_predict. So this is just creating predictions for each observation in our data based on the simulated draws from the posterior distribution for each of those coefficients. So it takes into account the estimation uncertainty as well as the predictive uncertainty, right? So we have individual predictions for each observation that take into account that uncertainty. Okay, we save this as a essentially as an array, and then create our PPC density overlay that includes both the actual outcome distribution that we observe plus our posterior predictive or simulated predictions from the posterior distribution, and we're just taking a sample of that because we don't want to take, plot all 4,000 densities. We'll just look at 100 draws from that posterior distribution. Okay, we're doing the same for our logarithmic transformation without the interaction, and then we'll check which one of those fits our data better, right? Which one of those distributions, posterior predictive distributions, resembles the outcome, the actual observed outcome measure better. Okay, and we're just combining both in a grid using base plot underscore grid here. Of course, all of these commands, as I mentioned before, are part of the base plot package. Okay, and this is the result. We see here first for our linear transformation with interaction, we see a clear deviation between our posterior predictive distribution and the actual observed distribution. Obviously, because the observed distribution y is bound at 0, we have no negative earnings. In our posterior predictive distribution, of course, we have quite a few observations where we would predict based on the linear model, predict basically negative earnings. The distribution is also quite skewed, obviously, as it is kind of common for any type of income and salary distribution. It's a very skewed distribution. So we see that our posterior predictive distribution doesn't really resemble the actual observed distribution. So we can kind of conclude from that this model doesn't really fit the underlying data generating process very well. It looks much better if we look at the posterior predictive checks for the logged outcome measure. Here we have obviously a much less skewed distribution. It is also not censored or bound on the logged scale. So we're resembling kind of we're kind of capturing the range of possible outcomes on the log scale quite well. Of course, there's still deviations. We have a somewhat bimodal distribution here in our actual observed outcome measure, and we only have a simple kind of approximately normal unimodal distribution for our posterior predictive distribution. If we, for example, took into account the interaction between gender and height, and potentially take into account additional covariates, we might be able to get a better sense of that as well. But just in this comparison between the simple model that just focuses on height and this interaction model that doesn't take into account the logarithmic transformation, we would say that this based on the posterior predictive checks, this model using the logged outcome measure fits the data much better. Okay. There are other types of transformations, just very quickly, that are discussed in the book chapter as well. For example, one transformation that is mentioned is the square root transformation, which can be useful. It's kind of similar to the logarithmic transformation, but it can be useful for compressing high values more mildly than is done by the logarithm, right? So this compression for extreme values is a little bit less strong for the square root transformation, so you can consider that as a possible alternative. But there are disadvantages. It lacks this clean interpretation in terms of percentage change that we talked about, and potentially induces non-monotonicity depending on the actual range of the data. Also, if we looked at square transformations, which would turn negative. So square root and square transformation, and for square transformations we have negative values that are then kind of, if we take the square of that, we turn that into a positive, large positive value, so that induces non-monotonicity in our outcome measure. So there can be problems with that. Okay. There are other types of idiosyncratic transformations depending on our specific, application, whatever kind of survey measures we have included. So you can think of different possible transformations tailored for specific problems if we want to combine certain, education categories or income groups and so on. So these are kind of idiosyncratic to whatever specific problem you're working with. In general, what we should take into account is in these cases, for example, I mean, I talked about the logarithmic transformation for income in our case here as being a little bit problematic because we're taking into account, or we basically have to drop all observations for which earnings are equal to 0. So we could kind of take into account and model the censoring and selection process by having first a dichotomous indicator, capturing whether we have earnings or whether there are no earnings, modeling that, and then modeling the actual value of the actual salary size, conditional on earnings being larger to 0. That would be an example of kind of a more idiosyncratic transformation that kind of takes into account the censoring process. We could also think of discrete coding that compresses extreme values, for example, building discrete categories for different income brackets that take into account kind of larger differences for extremer income values and so on, right? So there are lots of different options depending on your application, obviously. In general, one thing to kind of keep in mind is that sometimes it's also possible to use continuous underlying variables rather than discrete predictors. In the book, there's this example of left-handedness and right-handedness, which you could think of as a dichotomous indicator, but ultimately, if you measure left-handedness and right-handedness, you could kind of in a survey also measure this using a continuous scale. And so oftentimes many variables that appear binary or discrete can actually be usefully be viewed as continuous, and to the extent that you can measure them as continuous concepts, this actually ultimately captures more information. And so in most cases we want to avoid kind of converting underlying continuous variables into discrete categories because oftentimes we just basically throw away information. In some cases it's necessary to transform continuous measures into discrete categories, for example, to simplify a more complicated transformation or to take into account potential nonlinearity and so on. But as a general rule of thumb, we don't want to throw away information. So as soon as we have some continuous measure, we probably want to kind of take into account that continuous measure. Okay, so so much about transformations and different types of transformations. In the next video, I'm going to talk about building and comparing regression models for prediction.